So we have already established a stability criterion. We've said that if our process has this form in general, that we were concerned about any of these eigenvalues having a positive real part. Because if they do, then we will have the exponential of a positive number times t, and as t increases, then that term would exponentially explode away. And so if any of these lambdas have a positive real part, we know it would be an unstable process. And just to write that out a bit more explicitly, we can say let lambda I be, or rather lambda j, I see I use eventually. So we let lambda j be those eigenvalues, and let aj be the real part. And so we want aj always to be negative. And if we recall what we just saw with the Laplace transformations, the Laplace transform, we had it as e to the kt. We could equivalently do e to the lambda t. And if we just remind ourselves of what we did there, applying the standard Laplace transformation definition, we had grouped together the two terms. And when we integrated, we found that the solution was 1 over s minus lambda. And so we can see that the lambda shows up as the argument shift here in this function. So in the Laplace domain, the eigenvalue shows up in this way. And if we think about the meaning of lambda here, let's say when s equals lambda, we can see we've got 1 over 0, so that's going off to infinity. And so we call the s values where our function goes to infinity, we call that a pole. And that's a general term. It doesn't have to apply to Laplace transformation. For any function, let's say f of x, if there's an x value where the function goes to infinity, then we'll call that x value a pole, right? Because we can imagine we get, if we've got some function and then at one point it's shooting up to infinity, then that's like a pole sitting on our plane. So in this case, a pole is where s equals lambda. And so our criterion then is that if our pole has a positive real part, then we know we have this situation where A is positive, and we have that unfortunate situation where this is exploding off to infinity. So we can say our stability criterion is that the poles of our Laplace function must be negative. The real part of the pole must be negative, right? And that is, in effect, the Laplace equivalent of our stability criterion.